Episode 1: The Circuit of Crisis. From so simple a beginning, endless forms, most beautiful and most wonderful, have been, and are being, evolved. Charles Darwin. I am Vectorus. But to everyone I know, I am Dr. Albus Sinclair. Today I will introduce a new set of heroes known as the Quantum Six. This story begins in Atlanta, Georgia. The Atlanta skyline, a tapestry of modernity etched against a Georgian sunset, was alive with the buzz of drones and the glow of smart screens. Below, the city pulsed to the rhythm of Southern charm and high-tech promise. Yet, in the shadow of the towering Bank of America Plaza, nestled discreetly between the vibrant murals of the Beltline and the historic bricks of Sweet Auburn, was a building that whispered of secrets. This was the covert hub of the Quantum Six, a haven where the future was not just predicted, but shaped. On this particular day, as the city prepared for the evening's Braves game, and the air filled with the scent of barbecues, and the faint echo of jazz from the streets of Midtown, an alarm pierced the Quantum Six's lab. Enigma's latest ploy cast a dark cloud over the city, threatening more than just its digital tranquility. Michaela Jones, known to her team as Furia, paused her analysis of quantum algorithms and glanced at the sprawling OLED screens that dominated one wall of the lab. "Looks like Enigma's not just a fan of peaches and pecans," she quipped, her attempt at levity, belying the tension in her voice. Juan Gonzalez, Varino to the team, abandoned his examination of molecular models. "That's HealthNet's logo," he observed, pointing at the emblem now smeared with Cybertron's sinister sigil. "Every hospital from Emory University to Grady Memorial relies on their network." Anjali Patel Grovera stopped her work and joined the others. "If he hacks into HealthNet, that's not just patient privacy at risk. It's access to critical care protocols and pharmacy dispensations." Alex Zhang, known for his strategic acumen as Opterus, was already at the holographic interface, fingers flying over the light keys. "We need a plan. Cybertron's using Enigma to shake the pillars of trust in our system, and Atlanta is just the start." Devontae Henderson, Gunn, watched the digital map of Atlanta's network infrastructure unfold in the air before him. HealthNet's data center is in the heart of the city, right beneath the Weston Peachtree. It's the neural center of healthcare in the South. Shorebris, whose real name Clayton Lindbergh was rarely used outside of formalities, leaned back in his chair. "Enigma's not just knocking on the door, he's rewriting the building codes. We need to act fast." The Quantum Six were not just guardians of quantum mechanics. They were Atlanta's unseen protectors, operating in the space where technology and hope converged. To counter this threat, they would need to harness every qubit of their quantum knowledge. "Let's give the people of Atlanta a fighting chance," Furia declared. "We'll need to break this down: quantum circuits, qubits, superposition, entanglement. We'll teach, we'll fight, and we'll show Enigma that this city's more than a node in Cybertron's network." With the map of Atlanta still hovering before them, they plotted their strategy. From the sprawling campus of Georgia Tech to the bustling halls of Atlanta Tech Village, they would rally the brightest minds, turning every coder and hacker into a soldier in their quantum army. "Now listen up," Nagun addressed the select few who had pledged their intellect to the cause. "We'll start with the quantum circuit model. Think of it like the MARTA of quantum computing. It's the track on which every operation runs. We'll be the conductors, and we need you to help keep the trains running." The mission was clear: to educate and to protect. As the sun dipped below the horizon, painting the city in shades of fire and gold, the Quantum Six prepared to embark on their most crucial mission yet. Atlanta was more than a pin on the map. It was their home, and they would stand in defense of its future. "Tell me and I forget. Teach me and I remember. Involve me and I learn." Benjamin Franklin. Atlanta's night was a canvas of stars obscured by the city's radiant lights, from the shimmering facade of the Mercedes-Benz Stadium to the historic Fox Theater. The hum of the metropolis was usually comforting to the Quantum Six, a reminder of the life they were sworn to protect. But tonight, it was the backdrop to a dire countdown. In their clandestine lab, hidden beneath the guise of an abandoned textile mill in the West End, the Quantum Six stood encircled by screens aglow with cryptic quantum schematics. The air was tense, each member focused on the enormity of the task ahead. Verino's eyes were fixed on the holographic display of HealthNet's infrastructure, a complex network that spread through the city like the sprawling branches of an ancient oak. Enigma has embedded a sequence of quantum algorithms designed to slowly corrode the data's integrity, he said. It's like termites in the woodwork, except these are quantum termites. Faria nodded, her hands clasped behind her back as she considered their approach. Our usual brute force decryption won't work. This is a quantum lock. It needs a quantum key, which means we need to understand the locks he's using. Superposition and entanglement aren't just concepts, they're the tools of his trade, Grovera added, the reflection of equations flickering in her determined gaze. Opterus, ever the strategist, began to outline their plan. We need a two-pronged approach, educate and engage the public on quantum computing basics and dismantle Enigma's operations from within. Gunn stepped forward, his voice steady and assured. Let's start by breaking down the quantum circuit model for our new recruits. Atlanta's tech community is robust. They'll catch on quickly. Shorebris, the silent sentinel of cyberspace, finally spoke, his voice calm yet urgent. I'll start with the quantum gates. They're the building blocks of Enigma's circuit, and if we can understand them, we can dismantle them. The night stretched on as the Quantum Six worked tirelessly, their lab a beacon of resistance. They broadcasted tutorials masked as viral memes, used social media to disseminate beats of quantum facts, and gamified quantum concepts through popular Atlanta-based mobile apps. As dawn approached, the first signs of their efforts began to emerge. Code-savvy students from the Georgia Institute of Technology started forming think tanks, local hackerspaces organized virtual meetups, and even the data analysts from the Centers for Disease Control and Prevention lent their expertise to the cause. The city was waking up, not just to a new day, but to a new understanding of the quantum world. And as Atlanta rose, so did the hope that they could stand against Enigma's silent assault. The mind is not a vessel to be filled, but a fire to be kindled. Plutarch dawn had yet to break over the Atlanta skyline, where the tallest buildings like the SunTrust Plaza and Weston Peachtree Plaza stood like sentinels watching over a city not yet awake. The Quantum Six, however, had been up all night in their hidden lab. The pulsing blue and violet lights of their quantum computers reflected off the old brick walls, a stark contrast to the rustic charm of the city's historic Peachtree Street. Outside. This isn't just about protecting data. It's about safeguarding lives, Furia said solemnly, her gaze fixed on a holographic model of a quantum circuit. HealthNet's systems are more than records and numbers. They're the heartbeat of healthcare in Atlanta. Enigma's interference could be fatal. Verino nodded in agreement. Let's start with the basics of the quantum circuit model. We need everyone to understand, from the tech heads at the Atlanta Tech Village to the bright young minds at Spelman and Morehouse colleges. Grovera, her eyes bright with determination, began the lesson. In classical computing, we have bits. Here, in quantum computing, we deal with qubits. Unlike bits, which are like the switches on your traditional Peachtree trolley, either on or off, qubits can be in multiple states at once, thanks to superposition. Opterus interjected, think of it like the MARTA, where each train can be on every track simultaneously, until you look to see where it is. Gunn took over, his deep voice echoing in the stillness of the pre-dawn lab. Entanglement is another quantum phenomenon we utilize. If two qubits are entangled, like the paths of the Chattahoochee, intertwining through the city, the state of one qubit will instantly influence the other, no matter the distance between them. Shorebris, the tactical genius of the group, outlined their mission. Enigma is trying to hack HealthNet using these principles. He's creating a quantum circuit of chaos that could ripple out from Atlanta to the world. Verino gestured toward the holographic model floating before them. Every quantum computation has three elements: data, operations, and output. In this model, qubits are the data, quantum gates are the operations, and the output is what we measure at the end of the computation. The model shimmered, displaying a simple quantum circuit with three lines, each representing a qubit. We start with each qubit in the state chopper, explained Faria, which is our baseline, like the quiet stillness of the Atlanta Botanical Garden before the gates open. Grover pointed to the first symbol in the model, a small box labeled ZEED. This is a ZEED gate, she said. It's an operation that flips the phase of the qubit. In a way, it's like flipping the switch on Centennial Olympic Park's Fountain of Rings, changing the pattern of the water. As the team observed, Grover manipulated the virtual qubits, applying the ZEED gate to the first one. Next, we apply X, H, and Y gates to each qubit, respectively, she continued, demonstrating each gate. Think of these like the chefs in the kitchens of the Varsity, the Busy Bee, or Ponce City Market, each adding their own flavor to a dish. Opterus brought up the next part of the circuit. Here we have a 2-qubit gate, followed by a 3-qubit gate. These gates are like the junctions at Five Point Station, where multiple MARTA lines intersect and interact. Finally, Faria highlighted the end of the circuit, where 2 of the qubits were measured. The gauge symbol here represents measurement, the point at which we observe our qubits and see the results of our computation. It's like the sun rising over Stone Mountain, revealing the landscape that was shrouded in darkness. The team turned to their audience, a virtual gathering of Atlanta's brightest and bravest. Your mission, Shorebris addressed them, is to help us recreate this quantum circuit, to understand it, so we can predict Enigma's moves and counteract them. This is your Peachtree Road Race, your Dragon Con parade. This is your moment to shine for Atlanta and for the world. As the first light of morning filtered through the lab's skylight, casting long shadows across the room, the Quantum Six's message spread across the city, a call to arms for those willing to join the fight against the shadow looming over their beloved Atlanta. In the Quantum Six's lab, a symphony of clicking keyboards and murmured discussions filled the air, echoing off the sleek, high-tech walls. The team, laser-focused, worked tirelessly to decrypt Enigma's quantum puzzle, a complex weave of qubits and gates that held the key to preventing a catastrophic data breach. Opterus, his eyes scanning lines of quantum code, broke the silence. Let's delve deeper into the heart of this circuit. Understanding each component's role is crucial to unraveling Enigma's scheme. Faria, her fingers tracing over a holographic display of a quantum circuit, nodded in agreement. Right. We've covered the basic gates. Now let's talk about their sequences and combinations. It's like crafting a complex narrative. Every element has its place, its purpose. Grover joined in, her voice steady and clear. Imagine this. After applying our initial Z, X, H, and Y gates, we introduce a series of compound gates. It's these combinations that bring the real power of quantum computing to life. Verino pointed to a section of the circuit highlighted on the screen. Here's a 2-qubit gate, the cannot gate. It's pivotal in creating entanglement. Think of the control qubit as a key. When it's in a specific state, it unlocks a change in the target qubit. Shorebris chimed in, his tone analytical. C-naught gates are the cornerstone of many quantum algorithms. They're like a well-placed plot twist, changing the course of the story in unexpected ways. Gun, his gaze fixed on the intricate patterns of the circuit, added thoughtfully, remember, entanglement is what gives quantum computers their edge. It allows qubits to be interconnected, in a way that classical bits never can. As Furia observed their volunteers, many of whom were young coders and aspiring quantum physicists, she offered words of encouragement. Think of this circuit as a puzzle. Each gate, each line of code is a piece. Your job is to see how they fit together to form the bigger picture. The lab buzzed with renewed energy as the volunteers, guided by the Quantum Six, began to experiment with gate sequences, manipulating the virtual qubits with deft commands. They were not just learning, they were applying their knowledge in real time, a crucial step in their mission. Keep in mind the principle of reversibility, Verino reminded them. Every quantum operation can be undone. It's like retracing your steps in a complex maze, finding your way back to the start. Grover watched the screens, noting the volunteers' progress. And remember superposition. It's what allows our qubits to exist in multiple states simultaneously, a critical concept in understanding quantum computation's potential. As the morning turned to afternoon, the Quantum Six and their team continued their work, piecing together the puzzle of Enigma's quantum circuit. Each gate, each qubit, brought them closer to thwarting his plans. In the quiet focus of the lab, a plan was slowly taking shape, a strategy emerging from the chaos of quantum complexity. In the lab, a heightened sense of anticipation hung in the air. The Quantum Six, surrounded by their diligent volunteers, stood on the precipice of a groundbreaking moment. The quantum circuit, their collective brainchild, was ready to be deployed against Enigma's malicious plot. Let's review the possible ways this circuit can dismantle Enigma's plan, Furia began, her voice steady and confident. Understanding these mechanisms is crucial for our success. Verino stepped up to the holographic display. First, our circuit utilizes superposition to simultaneously process multiple possibilities. This allows us to rapidly sift through Enigma's quantum keys, identifying the correct configuration to unlock his encryption. Grover pointed to a section of the circuit. Here, we use entanglement to mirror Enigma's own strategy. By entangling our qubits in a similar pattern, we can create a counter-frequency that disrupts his quantum manipulations at their core. Opterus added, the inclusion of controlled rotation gates here is vital. They allow us to fine-tune the phase shifts in our qubits, effectively aligning them to negate the phase anomalies introduced by Enigma's circuit. Shorbris, analyzing the data, said, our Bell state measurements are the final piece of the puzzle. They will confirm the success of our disentanglement efforts and ensure that we've accurately replicated and inverted Enigma's circuit. Gunn, his eyes reflecting the glow of the quantum simulations, concluded, each aspect of this circuit has been designed to counteract Enigma's attack from multiple angles. It's a comprehensive solution to a complex problem. As the team prepared for the final deployment of the circuit, Furia turned to the volunteers. Before we proceed, let's test our understanding of what we've achieved. I have a 5-question multiple-choice quiz for you. The answers will be revealed in our next session. 1. What does the application of a Hadamard gate to a qubit in state Washu result in? A. The qubit remains in state Washu. B. The qubit moves to state 11C. The qubit is put into a state of superposition. D. The qubit is entangled with another qubit 2. Which gate is used for creating entanglement between two qubits? A. X gate. B. Z gate. C. Knot gate. D. H gate 3. What is the role of Bell state measurements in our quantum circuit? A. To apply phase shifts to qubits. B. To create superposition states. C. To confirm the success of disentanglement. D. To entangle qubits in a specific pattern. 4. Which concept allows a qubit to be in multiple states simultaneously? A. Entanglement. B. Superposition. C. Interference. D. Decoherence. 5. What happens to the state of a qubit after a measurement is performed? A. It becomes entangled with the measuring device. B. It remains in a superposition state. C. It collapses to either 0 or 1D. It reverses its phase. The Quantum Six's lab was a whirlwind of activity, with the team and their volunteers working tirelessly against the clock. The walls, lined with quantum circuit diagrams and complex mathematical equations, bore testament to the Herculean task at hand. Furia, her focus unwavering, reviewed the latest simulation results. We're getting closer. Our inverse circuit is starting to neutralize some of Enigma's manipulations, but we're not there yet. Verino, analyzing a series of quantum gate sequences, added, Enigma has layered his circuit with redundancy. It's like a multi-locked vault. Each gate sequence is a lock that needs to be picked. Grovera, her eyes tracing the flow of qubits, nodded in agreement. We need to refine our approach. Let's focus on the entanglement patterns. Disentangling them could be the key to exposing the core of his circuit. Opterus, his mind racing with strategies, suggested, we should also consider the timing of our gate applications. Quantum operations are delicate. Timing them perfectly could disrupt the coherence of Enigma's circuit. Shorbris, ever the cryptic strategist, pointed out, remember, in the quantum world, it's not just about what you do, but also when you do it. Our actions must be synchronized with the evolution of Enigma's circuit. Gun, his voice steady and calm, added, this is a quantum chess game, and we're several moves deep. Each decision has a cascade of consequences. We need to anticipate Enigma's next steps and be one step ahead. The lab buzzed with renewed energy as the team, guided by the Quantum Six, recalibrated their approach. Let's run another simulation, Furia directed. This time, pay close attention to the phase shifts and the entanglement patterns. We're looking for any anomalies, any weak points in Enigma's design. As the simulation ran, the team scrutinized every aspect of the circuit. The volunteers, now more confident in their understanding of quantum mechanics, contributed valuable insights, their fresh perspectives often illuminating overlooked details. Grovera, observing a particular sequence, remarked, here, the entanglement is weaker. If we apply a series of targeted gate operations, we might be able to unravel this section. Verino, working alongside her, nodded. Good catch. Let's apply a combination of Bell state measurements here. That might just break the entanglement and expose the underlying structure. The night wore on, and the lab became a symphony of collaborative efforts, each member playing their part in the intricate dance of quantum decryption. The Quantum Six, with their volunteers, were no longer just a team. They were a unified front against a formidable adversary. As dawn approached, a breakthrough seemed imminent. The latest simulation showed promising results, with parts of Enigma's circuit beginning to unravel under their strategic assault. We're close, Furia announced, her voice a mixture of exhaustion and excitement. Keep focused. Every qubit, every gate could be the difference between success and failure. The Quantum Six and their team pressed on, their determination fueled by the progress they had made. Enigma's quantum labyrinth was complex, but they were proving to be a worthy adversary. The battle of wits and intellect continued, each side pushing the boundaries of quantum understanding. Unity makes strength. English aphorism. The Quantum Six's lab, a nexus of frenetic activity and intense concentration, reflected the gravity of the situation. As they delved deeper into Enigma's quantum circuit, the complexity of his plan became more apparent, and so did the path to thwarting it. Enigma's circuit is not just a key to HealthNet's database, it's a constantly shifting maze, Opterus analyzed, his fingers tracing the flow of qubits on the screen. He's using a combination of quantum gates in a sequence that evolves over time, adapting to counter any standard decryption methods. Furia, her eyes locked on the holographic display, added, this adaptive nature is what makes it so challenging. It's like a chameleon changing its colors. As soon as you think you've figured it out, it transforms, Verino interjected, focusing on a series of operations in the circuit. Look here. Enigma's using a sequence of T-gates and S-gates, subtly altering the phases of the qubits. It's a sophisticated method to encode information within the quantum state. Grovera, her mind racing with possibilities, chimed in. These phase shifts are crucial. They're like hidden instructions within the circuit. If we can decode them, we can predict the circuit's evolution. Shorebris, always calm under pressure, pointed out, "Our advantage lies in understanding quantum interference. By carefully manipulating our own circuit, we can cause Enigma states to interfere destructively, effectively neutralizing his attack." Goon, deep in thought, added, "That means we need to construct a circuit that's the exact inverse of Enigma's. It's like composing a piece of music that perfectly cancels out another melody. Every note, every rhythm must align precisely." The team's focus shifted to constructing this inverse circuit. "We'll start by applying the inverse of the Hadamard gates, followed by the inverses of the T and S gates," Verino instructed, guiding the volunteers through the process. As the simulation ran, the circuit began to take shape, a mirror image of Enigma's creation. "Each qubit, each gate is a step towards unraveling his plan," Furia said with determination. Grovera monitored the evolving quantum states. "Watch the superposition of these qubits. As we apply our gates, we're slowly untangling the web Enigma has woven." The hours passed, and the lab became a crucible of quantum strategy. Each member of the Quantum Six, along with their team of volunteers, was fully engrossed in the task, their collective intellect a formidable force against Enigma's quantum machinations. Opterus, observing the unfolding scenario, remarked, "This is more than a battle of technology. It's a clash of minds, a contest of quantum wits, and we're winning." As night descended upon the lab, the team pressed on, their resolve unwavering. They were on the cusp of a breakthrough, a moment that could turn the tide in their favor. The simulation, a complex dance of light and shadow, continued to run, each iteration bringing them closer to decrypting Enigma's elusive quantum key. As the Quantum Six and their volunteers gathered in the lab, the tension was palpable. The final confrontation with Enigma was imminent. But first, they needed to consolidate their understanding of the quantum mechanics at play. Grovera, with a reassuring smile, began to review the answers to the quiz from their previous session. "Let's go over the answers to the quiz. This will not only reinforce our understanding, but also ensure we're all on the same page as we make our final move against Enigma," Grovera announced. 1. When a Hadamard gate is applied to a qubit in the Biwu state, what is the result? Answer: C. The qubit is placed into a superposition of Biwu and Wi1. Grovera explained, "The Hadamard gate is crucial for creating superposition, a fundamental property in quantum computing. It allows the qubit to exist in a state that is both 0 and 1 at the same time." 2. Which gate is essential for creating qubit entanglement? Answer: C. The Canot gate. Verino added, "The controlled NOT gate, or Canot, is fundamental in creating entangled states. It allows us to link the states of two qubits, such that the state of one directly influences the other." 3. What is the purposive Bell state measurements in our quantum circuit? Answer: B. To confirm the success of our entanglement disruption, Shorebris noted, Bell state measurements help us understand the success of our entanglement strategies. They're like a litmus test to check if our disentanglement process is working as intended. 4. Which quantum principle allows a qubit to exist in multiple states at once? Answer: B. Superposition. Gunn elaborated. Superposition is the cornerstone of quantum mechanics, allowing a qubit to exist in a blend of 0 and 1 states. It's this property that gives quantum computers their superior computational power over classical computers. 5. Upon measuring a qubit, what happens to its state? Answer: C. It collapses to either 0 or 1. Furia concluded, "Measurement in quantum mechanics is a unique phenomenon. When we measure a qubit, its superposed state collapses, resulting in a definite state of either L0 or L1. This collapse is fundamental to extracting useful information from a quantum system." As the team nodded in understanding, Opterus interjected, These principles are what make our quantum circuit capable of defeating Enigma. By manipulating superposition and entanglement and understanding the implications of measurement, we have designed a circuit that can neutralize his attack and safeguard HealthNet's data. Verino stepped forward, his eyes reflecting a determined resolve. Our strategy is set. With this circuit, we're not just breaking Enigma's encryption, we're using his own quantum tactics against him. It's a sophisticated dance of quantum states, and we're about to lead. The lab was abuzz with activity as the team began the final preparations for deploying their quantum circuit. Grover monitored the simulations, Verino checked the entanglement patterns, and Shorebris oversaw the sequence of operations. Gun and Furia coordinated the efforts, ensuring every aspect of the circuit was precisely tuned. "We're ready," Furia announced, her voice resonating with confidence. "It's time to put our plan into action. Let's bring an end to Enigma's scheme and protect what matters most." The Quantum Six, united in their purpose, initiated the deployment sequence. The room filled with a symphony of electronic whirs and beeps as the quantum computers came to life, processing the intricate quantum circuit that held the key to their victory. As the first rays of dawn broke through the lab's windows, casting a new light on their mission, the Quantum Six and their volunteers braced themselves for the final confrontation. The battle against Enigma was about to reach its climax. "Give us the tools, and we will finish the job." Winston Churchill. As the Quantum Six prepared for the final phase of their operation, the significance of their task weighed heavily on their minds. The lab, usually a place of scientific exploration, had transformed into the front line of a battle for data privacy, particularly within the healthcare sector. Furia, looking over the quantum circuit, addressed the team. "Remember, this is more than a technical challenge. Enigma's attack on HealthNet isn't just a breach of security. It's a threat to the sanctity of personal health information. It's a healthcare optimization problem at its core." Grovera, her expression serious, added, "Healthcare data is among the most sensitive and personal information. It's not just numbers and names. It's people's diagnoses, treatments, and histories. Protecting this data is paramount." Opterus, his hands folded, reflected on the broader implications. Data privacy in healthcare is a cornerstone of trust between patients and medical institutions. Enigma's scheme threatens to erode this trust, exploiting the very technology designed to safeguard it. Verino, examining the quantum circuit, said, "Our work here, using quantum computing, isn't just to counteract a threat. It's to demonstrate that the same technology can be used to protect and optimize healthcare systems." Shorebris, known for his strategic insights, spoke up. "Enigma's using quantum computing to exploit weaknesses in traditional encryption methods. Our countermeasure not only stops him but also opens doors to new ways of securing sensitive data." Guan, always contemplative, added, "The interplay of quantum computing and data privacy is a delicate balance. On one hand, quantum technology offers unparalleled potential for securing data. On the other, it presents new challenges that we must be prepared to face." Furia turned to the assembled volunteers. "Your contributions here go beyond solving a complex quantum puzzle. You're helping to shape the future of how sensitive healthcare data is protected." As the team worked, the gravity of their task became ever more apparent. They were not just defending against a quantum computing exploit, they were pioneering a new frontier in healthcare data security. "Our success here will be a beacon," Furia declared. "It will show that quantum computing can be a force for good, for protecting the most personal aspects of our lives." The Quantum Six, unified in their mission, continued their meticulous work. The deployment of their quantum circuit was more than a technical feat. It was a statement about the role of quantum computing in safeguarding the future of healthcare data privacy. As dawn broke, casting a new day's light into the lab, the Quantum Six stood ready for the final confrontation with Enigma. The air was charged with anticipation and a sense of purpose. Today, their profound understanding of quantum mechanics would be put to the ultimate test. "Initiate the counter circuit," Furia commanded, her voice steady and determined. The team's fingers flew across their control panels, activating the complex quantum circuit they had meticulously crafted. The lab's quantum processors began to hum with increased intensity, visualizing the battle of wits unfolding in the quantum realm. "We're engaging Enigma's circuit now," Verino announced, monitoring the flux of qubits on his screen. Gravera watched the entanglement patterns they had devised come to life. "Our entanglement strategy is countering his. It's a duel of quantum states, a dance of probability and precision." Shorbris, focused on the sequence of gates, added, "The synchronization of our gate operations is disrupting his circuit's coherence. Every phase shift, every rotation we've calculated is countering his manipulations." Opterus, his eyes on the evolving data, noted, "We're starting to see interference patterns. Our circuit is creating destructive interference in Enigma's quantum states, effectively nullifying his control over the data." Gun, observing the unfolding quantum duel, said, "The Bell state measurements are coming in. We're successfully breaking down his entangled states. It's working." As the team worked, the lab's main screen displayed a live quantum simulation. Enigma's circuit, a once menacing labyrinth of quantum complexity, was beginning to unravel, its secrets exposed by the precise countermeasures of the Quantum Six. Furia, her gaze locked on the simulation, declared, "We're close to breaking through. Keep the pressure up. Every qubit, every gate counts." The atmosphere in the lab was electric, each member of the team united in their resolve to defeat Enigma. The simulation showed their circuit gaining ground, dismantling Enigma's quantum web piece by piece. Suddenly, a series of rapid beeps erupted from the control panel. "We've done it," Grovera exclaimed. "Enigma's circuit has collapsed. His control over HealthNet's data is severed." A wave of relief and triumph swept through the lab. The Quantum Six had not only thwarted Enigma's plan, but had also demonstrated the incredible potential of quantum computing as a force for good. Furia addressed the team. "Today, we've not only saved countless lives by protecting their personal health data, but we've also paved the way for a new era in quantum computing, one where its power is harnessed for the protection and advancement of humanity." As the team celebrated their hard-won victory, the realization dawned that this was just the beginning. The quantum realm was vast and full of potential, both wondrous and daunting. But for now, the Quantum Six had proven that even in the face of immense challenges, unity, intellect, and perseverance could prevail. The basics of the quantum circuit model. We have mentioned that quantum computing relies on quantum phenomena, such as superposition, entanglement, and interference to perform computations. But what does this really mean? To make this explicit, we need to define a particular computational model that allow us to describe mathematically how to take advantage of all these properties. There are many such models, including quantum Turing machines, measurement-based quantum computing, also known as one-way quantum computing, or adiabatic quantum computing, and all of them are equivalent in power. However, the most popular one, and the one that we will be using for the most part in the book, is the quantum circuit model. To learn more, in addition to the quantum circuit model, sometimes we will also use the adiabatic model. All the necessary concepts will be introduced in Chapter 4, Quantum Adiabatic Computing and Quantum Annealing. Every computation has three elements: data, operations, and output. In the quantum circuit model, these correspond to some concepts that you may have already heard about qubits, quantum gates, and measurements. Through the remainder of this chapter, we will briefly review all of them, highlighting some special details that will be of particular importance when talking about quantum machine learning and quantum optimization algorithms. At the same time, we will show the notation that will be used throughout the book. But before committing to that, let us have a quick overview of what a quantum circuit is. Let's have a look at Figure 1. It shows a simple quantum circuit. The three horizontal lines that you see are sometimes called wires, and they represent the qubits that we are working with. Thus, in this case, we have 3 qubits. The circuit is meant to be read from left to right, and it represents all the different operations that are performed on the qubits. It is customary to assume that, at the very beginning, all the qubits are in state vertical bar 0 right angle. You do not need to worry yet about what vertical bar 0 right angle means, but please notice how we have indicated that this is indeed the initial state of all the wires by writing vertical bar 0 right angle to the left of each of them. Here is an example of a simple quantum circuit. In that circuit, we start by applying an operation called a Z gate on the top qubit. We will explain in the next section what all of these operations do, but note that we represent them with little boxes with the name of the operation inside. After that initial Z gate, we apply individual gates, X, H, and Y, on the top, middle, and bottom qubits, and then a 2-qubit gate on the top and middle qubits followed by a 3-qubit gate, which acts on all the qubits at the same time. Finally, we measure the top and bottom qubits. We will get to measurements in the next section, don't worry. And we represent this in the circuit using the gauge symbol. Notice that after these measurements, the wires are represented with double lines to indicate that we have obtained a result. Technically, we say that the state of the qubit has collapsed to a classical value. This means that from this point on, we do not have quantum data anymore, only classical bits. This collapse may seem a little bit mysterious, it is. But don't worry, in the next section, we will explain in detail the process by which quantum information, qubits, is transformed into classical data, bits. As you may have noticed, quantum circuits are somewhat similar to digital ones, in which we have wires representing bits and different logical gates, such as A and D, or and not acting on them. However, our qubits, quantum gates, and measurements obey the rules of quantum mechanics and show some properties that are not found in classical circuits. The rest of this chapter is devoted to explaining all of this in detail, starting with the simplest of cases, that of a single qubit, but growing all the way up to fully fledged quantum circuits that can use as many qubits and gates as desired. One advantage of using a computational model is that you can forget about the particularities of the physical implementation of your computer and focus instead on the properties of the elements on which you store information and the operations you can perform on them. For instance, we could define a qubit as a physical quantum system that is capable of being in 2 different states. In practice, it could be a photon with 2 possible polarizations, a particle with 2 possible values for its spin, or a superconducting circuit whose current can be flowing in one of 2 directions. When using the quantum circuit model, we can forget about those implementation details and just define a qubit as a mathematical vector. What is a qubit? In fact, a qubit, short for quantum bit, sometimes also written as qubit, or even qubit, is the minimal information unit in quantum computing. In the same way that a bit, short for binary digit, can be in state 0 or in state 1, a qubit can be in state vertical bar 0 right angle or in state vertical bar 1 right angle. Here, we are using the so-called Dirac notation, where these funny-looking symbols surrounding 0 and 1 are called qubits and are used to indicate that we are dealing with vectors instead of regular numbers. In fact, vertical bar 0 right angle and vertical bar 1 right angle are not the only possibilities for the state of a qubit, and, in general, it could be in a superposition of the form. A vertical bar 0 right angle plus B vertical bar 1 right angle, where AI and B are complex numbers called amplitudes, such that vertical bar A vertical bar squared plus vertical bar B vertical bar squared equals 1. The quantity square root of vertical bar A vertical bar squared plus vertical bar B vertical bar squared is called the norm or length of the state, and when it is equal to 1, we say that the state is normalized. To learn more, if you need a refresher on complex numbers or vector spaces, please check Appendix A, Complex Numbers, and Appendix B, Basic Linear Algebra. All these possible values for the state of a single qubit are vectors that live in a complex vector space. Of dimension 2, in fact, they live in what is called a Hilbert space, but since we will be working only with finite dimensions, there is no real difference. Thus, we shall fix the vectors vertical bar 0 right angle and vertical bar 1 right angle as elements of a special basis, which we will refer to as the computational basis. We will represent these vectors, constituents of the computational basis, as the column vectors vertical bar, 0 right angle equals, begin matrix 1 0 end matrix, vertical bar 1 right angle equals begin matrix 0 1 end matrix. And hence a vertical bar 0 right angle plus B vertical bar 1 right angle equals A begin matrix. 1 0 end matrix plus B begin matrix 0 1 end matrix equals begin matrix AB end matrix. If we are given a qubit and we want to determine, or rather estimate its state, all we can do is perform a measurement and get one of two possible results, 0 or 1. We have nonetheless seen how a qubit can be in infinitely many states. So how does the state of a qubit determine the outcome of a measurement? As you likely already know, in quantum physics, these measurements are not deterministic, but probabilistic. In particular, given any qubit, a vertical bar 0, right angle plus B vertical bar 1 right angle, the probability of getting 0 upon a measurement is vertical bar, a vertical bar squared, while that of getting 1 is vertical bar B, vertical bar squared. Naturally, these two probabilities must add up to 1, hence the need for the normalization condition vertical bar, a vertical bar squared, plus vertical bar B, vertical bar squared equals 1. If upon measuring a qubit we get, let's say, 0, we then know that after the measurement, the state of the qubit is vertical bar 0 right angle, and we say that the qubit has collapsed into that state. If we obtain 1, the state collapses to vertical bar 1 right angle. Since we are obtaining results that correspond to vertical bar 0 right angle and vertical bar 1 right angle, we say that we are measuring in the computational basis. Exercise 1. What is the probability of measuring 0 if the state of a qubit is square? Root of 1/2 vertical bar 0 right angle plus square root of 1/2 vertical bar 1 right angle. And the probability of measuring 1? What if the state of the qubit is square root of 1/3, vertical bar 0 right angle plus square root of 2/3, vertical bar 1 right angle? And if it is square root of 1/2 vertical bar 0 right angle minus square root of 1/2 vertical bar 1 right angle? So, a qubit is, mathematically, just a two-dimensional vector that satisfies a normalization condition. Who could have known? But the surprises do not end here. In the next subsection, we will see how we can use those funny-looking kets to compute inner products in a very easy way. 1.3. Dirac notation and inner products. Dirac notation can not only be used for column vectors, but also for row vectors. In that case, we talk of bras, which together with kets can be used to form brackets. This name is a pun because, as we are about to show, brackets are, in fact, inner products that are written, you guessed it, between brackets. To be more mathematically precise, with each ket we can associate a bra that is its adjoint or conjugate transpose or Hermitian transpose. In order to obtain this adjoint, we take the ket's column vector, we transpose it and conjugate each of its coordinates, which are, as we already know, complex numbers. We use left angle 0, right vertical bar, to denote the bra associated with vertical bar, 0 right angle and left angle 1, right vertical bar to denote the bra associated with vertical bar, 1 right angle, so we have left angle 0, right, vertical bar equals vertical bar, 0 right angle, dagger equals begin, matrix 1, 0 end matrix dagger equals begin matrix 1 and 0 end matrix, left angle 1 right, vertical bar equals vertical bar, 1 right angle, dagger equals begin matrix 0 1 end. Matrix dagger equals begin matrix 0 and 1 end matrix and, in general, a left angle 0 right vertical bar plus B left angle 1 right vertical bar equals a vertical bar 0 right angle dagger plus B vertical bar, 1 right angle, dagger equals a begin matrix 1 and 0 end matrix, plus B begin matrix 0 and 1 end matrix equals begin matrix AB end matrix, where, as it is customary, we use the dagger symbol, dagger, for the adjoint. Important note. When finding the adjoint, do not forget to conjugate the complex numbers. For instance, it holds that begin matrix 1 minus I over 2, I over square root of 2 end matrix dagger equals begin matrix 1 plus I over 2 minus I over square root of 2 end matrix. One of the reasons why Dirac notation is so popular for working with quantum systems is that, by using it, we can easily compute the inner products of kets and bras. For instance, we can readily show that left angle 0 vertical bar 0 right angle equals 1, left angle 0 vertical bar 1 right angle equals 0, left angle 1 vertical bar 0 right angle equals 0, left angle 1 vertical bar 1 right angle equals 1. This proves that vertical bar 0 right angle and vertical bar 1 right angle are not just elements of any basis but of an orthonormal one, since vertical bar 0 right angle and vertical bar 1 right angle are orthogonal and of length 1. Thus, we can compute the inner product of two states. Vertical bar psi sub 1 right angle equals a vertical bar 0 right angle plus b vertical bar 1 right angle and vertical bar psi sub 2 right angle equals c vertical bar 0 right angle plus d vertical bar 1 right angle. Using Dirac notation by noting that left angle psi sub 1 vertical bar psi sub 2 right angle equals a asterisk c plus b asterisk d, where a asterisk and b asterisk are the complex conjugates of a and b. Exercise 1.2. What is the inner product of square root of 1/2 vertical bar 0 right angle plus square root of 1/2 vertical bar 1 right angle and square root of 1/3 vertical bar 0 right angle plus square root of 2/3 vertical bar 1 right angle, and the inner product of square root of 1/2 vertical bar 0 right angle plus square root of 1/2 vertical bar 1 right angle and square root of 1/2 vertical bar 0 right angle minus square root of 1/2 vertical bar 1 right angle. To learn more, notice that if vertical bar psi right angle equals a vertical bar 0 right angle plus b vertical bar 1 right angle, then vertical bar left angle 0 vertical bar psi right angle. Vertical bar squared equals vertical bar squared, which is the probability of measuring 0 if the state is vertical bar psi right angle. This is not accidental. In Chapter 7, VQE, Variational Quantum Eigensolver, for example, we will use measurements in orthonormal basis other than the computational one. And we will see how, in that case, the probability of measuring the result associated to an element vertical bar phi right angle of a given orthonormal basis is exactly vertical bar left angle, phi vertical bar, psi right angle, vertical bar squared. We now know what qubits are, how to measure them, and even how to benefit from Dirac notation for some useful computations. The only thing remaining is to study how to operate on qubits. Are you ready? It is time for us to get you introduced to the mighty quantum gates. 1-qubit quantum gates. So far, we have focused on how a qubit stores information in its state and on how we can access part of that information with measurements. But in order to develop useful algorithms, we also need some way of manipulating the state of qubits to perform computations. Since a qubit is, fundamentally, a quantum system, its evolution follows the laws of quantum mechanics. More precisely, if we suppose that our system is isolated from its environment, it obeys the famous Schrödinger equation. To learn more, the time-independent Schrödinger equation can be written as h vertical bar psi of t right angle equals I h bar d over dt vertical bar psi of t right angle, where h is the Hamiltonian of the system. Vertical bar psi of t right angle is the state vector of the system at time t, I is the imaginary unit, and h bar is the reduced Planck constant. We will talk more about Hamiltonians in Chapter 3, QUBO, Quadratic Unconstrained Binary Optimization, Chapter 4, Quantum Adiabatic Computing and Quantum Annealing, and Chapter 7, VQE, Variational Quantum Eigensolver. Don't panic. To program a quantum computer, you don't need to know how to solve Schrödinger's equation. In fact, the only thing that you need to know is that its solutions are always a special type of linear transformations. For the purposes of the quantum circuit model, since we are working in finite dimensional spaces and we have fixed a basis, the operations can be described by matrices that are applied to the vectors that represent the states of the qubits. But not any kind of matrix does the trick. According to quantum mechanics, the only matrices that we can use are the so-called unitary matrices, which are the matrices U, such that U dagger U equals U, U dagger equals I, where I is the identity matrix and U dagger is the adjoint of U, that is, the matrix obtained by transposing U and replacing each element by its complex conjugate. This means that any unitary matrix U is invertible, and its inverse is given by U dagger. In the context of the quantum circuit model, the operations represented by these matrices are called quantum gates. To learn more, it is relatively easy to check that unitary matrices preserve vector lengths. See, for instance, section 5.7.5 in Dancing with Qubits by Robert Souter, 92. That is, if U is a unitary matrix and vertical bar psi right angle is a quantum state, and hence its norm is 1, as we already know, then U vertical bar psi right angle also is a valid quantum state because its norm is still 1. For this reason, we can safely apply unitary matrices to our quantum states and rest assured that the resulting states will satisfy the normalization condition. When we have just one qubit, our unitary matrices need to be of size 2 by 2 because the state vector is of dimension 2. Thus, the simplest example of a quantum gate is the identity matrix of dimension 2, which transforms the state of the qubit by not transforming it at all. A less boring example is the X gate, whose matrix is given by X equals begin P matrix 0 and 1 1 and 0 end P matrix. The X gate is also called the NOT gate because its action on the elements of the computational basis is X vertical bar 0 right angle equals vertical bar 1 right angle. X vertical bar 1 right angle equals vertical bar 0 right angle, which is exactly what the NOT gate does in classical digital circuits. Exercise 1.3. Check that the gate X matrix is, indeed, unitary. What is the inverse of X? What is the action of X on a general qubit in a state of the form a vertical bar 0 right angle plus B vertical bar 1 right angle? A quantum gate with no classical analog is the Hadamard or H gate, given by H equals begin P matrix 1 over square root of 2 and 1 over square root of 2, 1 over square root of 2, and minus 1 over square root of 2. End P matrix equals 1 over square root of 2, begin P matrix 1 and 1 1 and minus 1 end P matrix. This gate is extremely useful in quantum computing, for it can create superposition. To be precise, if we apply the H gate on a qubit in state vertical bar 0 right angle, we obtain H vertical bar 0 right angle equals 1 over square root of 2 vertical bar 0 right angle plus 1 over square root of 2 vertical bar 1 right angle equals 1 over square root of 2, left parenthesis vertical bar 0 right angle, plus vertical bar 1 right angle, right parenthesis. This state is so important that it has its own name and symbol. It is called the plus state, and it is denoted by vertical bar plus right angle. In a similar way, we have that H vertical bar 1 right angle equals 1 over square root of 2 left parenthesis vertical bar 0 right angle minus vertical bar 1 right angle. Right parenthesis, and, as you probably guessed, this state is called the minus state, and it is denoted by vertical bar minus right angle. Exercise 1.4. Check that the gate H matrix is, indeed, unitary. What is the action of H on vertical bar plus right angle and vertical bar minus right angle? What is the action of X on vertical bar plus right angle and vertical bar minus right angle? Of course, we can apply several gates to the same qubit one after the other. For instance, consider the following circuit, HXH. We read gates from left to right, so in the preceding circuit we would first apply an H gate, then an X gate, and finally another H gate. You can easily check that if the initial state of the qubit is vertical bar 0 right angle, it would end up again in state vertical bar 0 right angle. But were its initial state vertical bar 1 right angle, the final state would become minus vertical bar 1 right angle. It turns out that this operation is also very important, and of course it has its own name. We call it the Z gate. From its action on vertical bar 0 right angle and vertical bar 1 right angle, we can tell that its matrix will be Z equals begin P matrix 1 and 0 0 and minus 1 end P matrix, something that we could have also deduced by multiplying the matrices of the gates, H, X, and H, one after the other. Exercise 1.5. Check that Z vertical bar 0 right angle equals vertical bar 0 right angle, and that Z vertical bar 1 right angle equals minus vertical bar 1 right angle in two different ways. First, use Dirac notation and the actions of H and X. Remember that we have defined Z as HXH. Then, derive the same result by performing the matrix multiplication. Begin P matrix 1 over square root of 2 and 1 over square root of 2 1, over square root of 2 and minus 1 over square root of 2, and P matrix begin P matrix 0 and 1 1 and 0 and P matrix begin P matrix 1 over square root of 2 and 1, over square root of 2 1 over square root of 2 and minus 1 over square root of 2 NP a matrix. Since there are X and Z gates, you may be wondering if there is also a Y gate. Indeed, there is one given by matrix Y equals begin P matrix 0 and minus II and 0 NP a matrix. To learn more, the set I, X, Y, Z, known as the set of Pauli matrices, is of great importance in quantum computing. One of its many interesting properties is that it constitutes a basis of the vector space of 2 by 2 complex matrices. We will work with it in Chapter 7 VQE, variational quantum eigensolver, for instance. Other important 1-qubit gates include the S and T gates, whose matrices are S equals begin P matrix 1 and 0 0 and e to the IPI over 2 and P matrix T equals begin P matrix 1 and 0 0 and e to the I pi over 4 and P matrix. But, of course, there is an uncountably infinite number of two-dimensional unitary matrices, and we cannot just list them all here. What we will do instead is introduce a beautiful geometrical representation of single-qubit states, and with it, we will explain how all 1-qubit quantum gates can, in fact, be understood as certain kinds of rotations. Enter the Bloch sphere. Exercise 1.6. Check that T squared equals S. Then, use the most beautiful formula ever, i.e. Euler's identity. E to the IPI plus 1 equals 0. To check that S squared equals Z, check also that S and T are unitary. Express S dagger and T dagger as powers of S and T. 1.3.4. The Bloch sphere and rotations. The general state of a qubit is described with two complex numbers. Since each of those numbers has two real components, it would be natural to think that we would need a four-dimensional real space in order to represent the state of a qubit. Surprisingly enough, all the possible states of a qubit can be drawn on the surface of an old-school sphere, which is a two-dimensional object. To show how it can be accomplished, we need to remember that a complex number z can be written in polar coordinates as z equals re to the I alpha, where r equals vertical bar. Z vertical bar is a non-negative real number, and alpha is an angle in 0, 2 pi. Consider then a qubit in a state vertical bar psi right angle equals a vertical bar 0 right angle plus b vertical bar 1 right angle, and write a and b in polar coordinates as a equals r sub 1 e to the I alpha sub 1, b equals r sub 2 e to the I alpha sub 2. We know that r sub 1 squared plus r sub 2 squared equals vertical bar. A vertical bar squared plus vertical bar b, vertical bar squared equals 1, and since 0 less than or equal to r sub 1, r sub 2 less than or equal to 1, there must exist an angle theta in 0 pi, such that cos theta 2 equals r sub 1 and sin theta 2 equals r sub 2. The reason for considering theta 2 instead of theta in the cosine and sin will be apparent in a moment. Notice that by now we have vertical bar psi right angle equals cos theta 2, e to the I alpha sub 1 vertical bar 0 right angle plus sin theta 2, e to the I alpha sub 2 vertical bar 1 right angle. Another crucial observation is that we can multiply vertical bar psi right angle by a complex number c, with absolute value 1 without changing its state. Indeed, it is easy to see that c does not affect the probabilities of obtaining 0 and 1 when measuring in the computational basis, check it. And by linearity, it comes out when applying a quantum gate u, that is, uc vertical bar psi right angle, equals cu vertical bar psi right angle. Thus, there is no operation, either unitary transformation or measurement, that allows us to distinguish vertical bar psi right angle from c vertical bar psi right angle. We call C a global phase, and we have just shown that it is physically irrelevant. Important note. Notice, however, that relative phases are, unlike global ones, really relevant. For instance, vertical bar plus right angle equals 1 over square root of 2, vertical bar 0 right angle plus vertical bar 1 right angle, and vertical bar minus right angle equals 1 over square root of 2, vertical bar 0 right angle minus vertical bar 1 right angle. Differ just in the phase of vertical bar 1 right angle. But we can easily distinguish between them by first applying h to those states, and then measuring them in the computational basis. We can, thus, multiply vertical bar psi right angle by e to the minus I alpha sub 1 to obtain an equivalent representation. Vertical bar psi right angle equals cos theta 2, vertical bar 0 right angle, plus sin theta 2 e to the I phi vertical bar 1 right angle, where we have defined phi equals alpha sub 2 minus alpha sub 1. In this way, we can describe the state of any qubit with just two numbers, theta in 0, pi, and phi in 0, 2 pi, that we can interpret as a polar angle and an azimuthal angle, respectively. That is, we are using what are known as spherical coordinates. This gives us a three-dimensional point, sin theta, cos phi, sin theta, sin phi, cos theta, that locates the state of the qubit on the surface of a sphere, called the Bloch sphere. See Figure 1.2. Figure 1.2, qubit, state vertical bar, psi, right angle represented on the Bloch sphere. Notice that theta runs from 0 to pi to cover the whole range from the top to the bottom of the sphere. This is why we use theta 2 in the representation of our preceding qubit. We only needed to get up to pi 2 for our angles in the sines and cosinas. In the Bloch sphere, vertical bar 0 right angle is mapped to the north pole and vertical bar 1 right angle to the south pole. In general, states that are orthogonal with respect to the inner product are antipodal on the sphere. For instance, vertical bar plus right angle and vertical bar minus right angle both lie on the equator, but on opposite points of the sphere. As we already know, the x-gate takes vertical bar 0 right angle to vertical bar 1 right angle and vertical bar 1 right angle to vertical bar 0 right angle, but leaves vertical bar plus right angle and vertical bar minus right angle unchanged, at least up to an irrelevant global phase. In fact, this means that the x-gate acts like a rotation of pi radians around the x-axis of the Bloch sphere. So now you know why we use that name for the gate. In the same manner, z and y are rotations of pi radians around the z and y axes, respectively. We can generalize this behavior to obtain rotations of any angle around any axis of the Bloch sphere. For instance, for the x, y, and z axes, we may define r sub x, theta, equals e to the minus I theta over 2x equals cos theta 2, I minus I sin theta 2, x equals begin p a matrix cos theta 2, and minus I sin theta 2, minus I sin theta 2, and cos theta 2, n p matrix, r sub y theta, equals e to the minus I theta over 2y equals cos theta 2, I minus I sin theta 2, y equals begin, p matrix cos theta 2, and minus sin theta 2, and cos theta 2, and p matrix, r sub z theta, equals e to the minus I theta over 2z equals cos theta 2, I minus I sin theta 2, z equals begin, p matrix e to the minus I theta over 2 and 0, 0 and e to the theta over 2, n p matrix equivalent begin, p matrix 1 and 0, 0 and e to the e theta n p matrix, where we use the equivalent symbol for equivalent action up to a global phase. Notice that r sub x, pi, equivalent x, r sub y, pi, equivalent y, r sub z, pi, equivalent z, r sub z, pi, 2, equivalent s, and r sub z, pi, 4, equivalent t. Exercise 1.7. Check these equivalences by substituting the angles in the definitions of r sub x, r sub y, and r sub z. In fact, it can be proved, see for instance the book by Nielsen and Chuang, 69s, that for any one qubit gate U, there exists a unit vector, r equals r sub x, r sub y, r sub z, and an angle theta, such that U equivalent cos theta 2, I minus I sin theta 2, r sub xx plus r sub y, y plus r sub zz. For example, choosing theta equals pi and r equals 1 square root of 2, 0, 1 square root of 2. We can obtain the Hadamard gate, for it holds that h equivalent minus I x plus z square root of 2. Additionally, it can also be proved that, again for any one qubit gate U, there exist three angles alpha, beta, and gamma, such that U equivalent r sub z, alpha, r sub y, beta, r sub z, gamma. In fact, you can obtain such a decomposition for any two rotation axes, as long as they are not parallel, not just for y and z. Moreover, in some quantum computing architectures, including the ones used by companies such as IBM, it is common to use a universal one-qubit gate, called the U-gate, that depends on three angles and is able to generate any other one-qubit gate. Its matrix is U, theta, phi, lambda, equals begin P matrix cos theta 2, and minus E2, the I, lambda, sin theta 2, e to the I phi sin theta 2, and e to the I, phi plus lambda, cos theta 2, and P matrix. Exercise 1.8. Show that U, theta, phi, lambda is unitary. Check that R sub x, theta, equals U, theta, minus PA2, PA2, that R sub y, theta, equals U, theta, 0, 0. And that up to a global phase U theta equals R sub z, 0, 0 theta. All these observations about how to construct one-qubit gates from rotations and parametrized families will be very important when we talk about variational forms and feature maps in Chapter 9, quantum support vector machines, and Chapter 10, quantum neural networks, and also to construct controlled gates later in this chapter. 1.3.5. Hello, quantum world. To put together everything that we have learned, we are going to create our very first complete quantum circuit. It looks like this. H. It doesn't seem very impressive, but let's analyze it part by part. As you know, following convention, the initial state of our qubit is assumed to be vertical bar 0 right angle, so that's what we have before we do anything. Then we apply the H-gate, so the state changes to square root of 1/2 vertical bar. 0 right angle plus square root of 1/2 vertical bar, 1 right angle. Finally, we measure the qubit. The probability of obtaining 0 will be vertical bar, square root of 1/2 vertical bar squared, which is 1/2, and that of getting 1 will also be 1/2. So we have created a circuit that, at least in theory, generates random bits following a perfectly uniform distribution. To learn more, unbiased uniform bit distributions are of great relevance for multiple applications in simulation, cryptography, and even online gambling games. As we will learn in Chapter 2, the tools of the trade, current quantum computers deviate from this equilibrium because they are affected by noise and gate and measurement errors. However, protocols to extract perfect random bits even with noisy quantum computers have been proposed and could become one of the first practical applications of quantum computing. See, for instance, the paper by Atzin and Massanes. We can modify the previous circuit to obtain any distribution over 0 and 1 that we desire. If we want the probability of measuring 0 to be p in 0, 1, we just need to consider theta equals 2 arcos square root of p, and the following circuit, r sub y, theta, exercise 1.9. Check that. With the preceding circuit, the state before measurement is square root of p vertical bar, 0 right angle plus square root of 1 minus p vertical bar, 1 right angle. And, hence, the probability of measuring 0 is p, and that of measuring 1 is 1 minus p. For now, this is all that we need to know about 1-qubit states, gates, and measurements. Let us move on to 2-qubit systems, where the mysteries of entanglement are awaiting to be revealed. 1.4, working with 2 qubits and entanglement. Now that we have mastered the inner workings of solitary qubits, we are ready to up the ante. In this section, we will learn about systems of 2 qubits and how they can become entangled. We will first define the mathematical representation of 2-qubit systems and how we can measure them. After that, we will study different quantum gates that can act on 2 qubits at once, and we will have a look at some of their very interesting and slightly puzzling properties. We will conclude with a simple but enlightening example of a 2-qubit circuit. We promise that the ride is going to be amazing. 1.4.1. 2-qubit states. So far, we have worked with qubits in isolation. But the real power of quantum computing cannot be unleashed unless qubits can talk to each other. We will start by considering the simplest case of quantum systems in which there is qubit interaction. 2-qubit systems. Of course, in a 2-qubit system, each of the qubits can be in state vertical bar 0 right angle or in state vertical bar 1 right angle. Thus, for the 2 qubits, we have 4 possible combinations. Both are in state vertical bar 0 right angle. The first one is in state vertical bar 0 right angle, and the second one in state vertical bar 1 right angle. The first one is in state vertical bar 1 right angle, and the second one in state vertical bar 0 right angle, or both are in state vertical bar 1 right angle. These 4 possibilities form a basis, called the computational basis, of a 4-dimensional space, and we denote them, respectively, by vertical bar 0 right angle tensor, vertical bar 0 right angle, vertical bar 0 right angle, tensor, vertical bar, 1 right angle, vertical bar 1 right angle, tensor, vertical bar 0 right angle, vertical bar 1 right angle, tensor, vertical bar 1 right angle. Here, tensor is the symbol for the tensor product. The tensor product of 2 column vectors is defined by begin P matrix, a sub 1, a sub 2 V dots, a sub n P matrix tensor begin P matrix B, sub 1 B sub 2 V dots B, sub m n P matrix equals begin P matrix a sub 1 begin P matrix B a sub 1 B sub 2 V dots B sub m n P matrix a sub 2 begin P matrix B sub 1 B sub 2 V dots B sub m n P matrix V dots a sub n begin P matrix B sub 1 B sub 2 V dots B sub m n P matrix equals begin P matrix a sub 1 B sub 1 a sub 1 B sub 2 V dots a sub 1 B sub m a sub 2 B sub 1 a sub 2 B sub 2 V dots a sub 2be sub m v dots, a sub nbe sub 1 a sub nbe sub 2 v dots, a sub nbe sub mnp matrix. Hence, the four basis states can be represented by four-dimensional column vectors given by vertical bar, 0 right angle tensor. Vertical bar 0 right angle equals begin p matrix 1 0 0 0 end. P matrix vertical bar 0 right angle tensor vertical bar 1 right angle equals begin p matrix 0 1 0 0 end. P matrix vertical bar 1 right angle tensor vertical bar 0 right angle equals begin p matrix 0 0 1 0 end. P matrix vertical bar 1 right angle tensor vertical bar 1 right angle equals begin P matrix 0 0 0 1 end P matrix. Usually we omit the tensor symbol and just write vertical bar 0 0 right angle, vertical bar 0 1 right angle, vertical bar 1 0 right angle, vertical bar 1 1 right angle, or vertical bar 0 0 right angle, vertical bar 0 1 right angle, vertical bar 1 0 right angle, vertical bar 1 1 right angle, or even vertical bar 0 right angle, vertical bar 1 right angle, vertical bar 2 right angle, vertical bar 3 right angle. Obviously, in this last case, the number of qubits that we are using must be clear from the context in order not to mistake the state, vertical bar 0 right angle of a 1-qubit system, with the state vertical bar 0 right angle of a 2-qubit system, or, as we will see soon, any other multi-qubit system. As we have mentioned, these four states constitute a basis of the vector space of possible states for a 2-qubit system. The general expression for the state of such a system is vertical bar psi right angle equals a sub 0 0 vertical bar 0 0 right angle plus a sub 0 1 vertical bar 0 1 right angle plus a sub 1 0 vertical bar 1 0 right angle plus a sub 1 1 vertical bar 1 1 right angle, where a sub 0 0, a sub 0 1, a sub 1 0, and a sub 1 1 are complex numbers called amplitudes, remember? Such that the sum from x equals 0 to 1, sum from y equals 0 to 1, vertical bar a sub xy vertical bar squared equals 1. If we measure in the computational basis both qubits at this generic state that we are considering, we will obtain 0 0, with probability vertical bar a sub 0 0 vertical bar squared, 0 1 with probability vertical bar a sub 0 1 vertical bar squared, 1 0 with probability vertical bar a sub 1 0 vertical bar squared, and 1 1 with probability vertical bar a sub 1 1 vertical bar squared. In all those cases, the state will collapse to the state corresponding to the outcome of the measurement, just as with 1-qubit systems. Let's now say that we only measure one of the qubits. What happens then? Suppose that we measure the first qubit. Then, the probability of obtaining 0 will be vertical bar a sub 0 0 vertical bar squared plus vertical bar a sub 0 1 vertical bar squared, which is the sum of the probabilities of all the outcomes in which the first qubit can be 0. If we measure the first qubit, and the result turns out to be 0, the system will not collapse completely, but it will remain in the state a sub 0 0 vertical bar 0 0 right angle plus a sub 0 1 vertical bar 0 1 right angle. Square root of vertical bar a sub 0 0 vertical bar squared plus vertical bar a sub 0 1 vertical bar squared, where we have divided by the square root to keep the state normalized. The situation in which the result of the measurement is 1 is analogous. Exercise 1.10. Derive the formulas for the probability of measuring 1 on the first qubit in a general 2-qubit state and for the state of the system after the measurement. Dirac notation is also useful to compute inner products of 2-qubit states. We only need to notice that left angle psi sub 1 right vertical bar tensor, left angle psi sub 2 right vertical bar phi sub 1 right angle, tensor vertical bar phi sub 2 right angle equals left angle, psi sub 1 vertical bar phi sub 1 right angle left angle, pc sub 2 vertical bar phi sub 2 right angle. Apply distributivity and remember to conjugate the complex coefficients when obtaining a Birra from a ket. Then, for instance, we can notice that the inner product of 4 5 vertical bar 0 1 right angle plus 3 e5 vertical bar 1 1 right angle and 1 square root of 2 vertical bar 0 0 right angle plus 1 square root of 2 vertical bar 1 1 right angle is 4 5 left angle 0 1 right vertical bar 3 I5 left angle 1 1 right vertical bar 1 square root of 2 vertical bar 0 0 right angle plus 1 square root of 2 vertical bar 1 1 right angle equals 4 5 square root of 2 left angle 0 1 vertical bar 0 0 right angle plus 4 5 square root of 2, left angle, 0 1, vertical bar, 1 1 right angle, 3i 5 square root of 2, left angle, 1 1 vertical bar, 0 0 right angle, 3i 5 square root of 2, left angle, 1 1 vertical bar, 1 1 right angle equals 4 5 square root of 2, left angle, 0 vertical bar, 0 right angle, left angle 1, vertical bar, 0 right angle, plus 4 5 square root of 2, left angle, 0 vertical bar, 1 right angle, left angle 1 vertical bar, 1 right angle, 3 I 5 square root of 2, left angle 1 vertical bar, 0 right angle, left angle 1 vertical bar, 0 right angle, 3 I 5 square root of 2, left angle 1 vertical bar, 1 right angle, left angle 1 vertical bar, 1 right angle, equals 3 I 5 square root of 2, since left angle 0, vertical bar 1 right angle equals left angle, 1 vertical bar 0, right angle equals 0 and left angle, 0 vertical bar, 0 right angle equals left angle 1, vertical bar 1 right angle equals 1. 1.4.2 2-qubit gates, tensor products. Of course, the operations that we can conduct on 2-qubit systems need to be unitary. Thus, 2-qubit quantum gates are 4x4 unitary matrices that act on 4-dimensional column vectors. The simplest way to construct such matrices is by taking the tensor product of two 1-qubit quantum gates. Namely, if we consider two 1-qubit gates, U sub 1 and U sub 2 and 2, 1-qubit states, vertical bar psi sub 1 right angle and vertical bar psi sub 2 right angle, we can form a 2-qubit gate. U sub 1 tensor U sub 2, that acts on vertical bar psi sub 1 right angle, tensor vertical bar psi sub 2 right angle as U sub 1 tensor U sub 2, vertical bar psi sub 1 right angle, tensor vertical bar psi sub 2 right angle, equals U sub 1 vertical bar psi sub 1 right angle, tensor U sub 2 vertical bar psi sub 2 right angle. By linearity, we can extend U sub 1 tensor U sub 2 to any combination of 2-qubit states, and we can associate a matrix to U sub 1 tensor U sub 2. In fact, said matrix is given by the tensor product of the matrices associated to U sub 1 and U sub 2. More concretely, the expression for the tensor product A tensor B of the 2x2 matrices, A and B, is begin P matrix, a sub 11 and a sub 12, a sub 21 and a sub 22, and P matrix, tensor begin P matrix, B, sub 11 and B sub 12, B sub 21 and B sub 22, and P matrix equals, begin P matrix, a sub 11 begin P matrix, B sub 11 and B sub 12, B sub 21 and B sub 22, and P matrix A sub 12, begin P matrix B sub 11 and B sub 12, B sub 21 and B sub 22, and P matrix A sub 21. Begin P matrix B sub 11 and B sub 12, B sub 21 and B sub 22, and P matrix A sub 22. Begin P matrix B sub 11 and B sub 12, B sub 21 and B sub 22. And P matrix and P matrix. Now it is easy to verify that this operation is indeed unitary and, hence, deserves the name of quantum gate. Exercise 1.11. Check that, given any pair of unitary matrices U sub 1 and U sub 2, the inverse of U sub 1 tensor U sub 2 is U sub 1 dagger tensor U sub 2 dagger, and that U sub 1 tensor U sub 2 dagger equals U sub 1 dagger tensor U sub 2 dagger. Tensor products of gates occur naturally when we have circuits with 2 qubits and pairs of individual 1-qubit gates are acting on each of them. For instance, in the following circuit, the gate X tensor X acts on the 2 qubits, and then it is followed by the gate H tensor I, where I is the identity gate, XHX exercise 1.12. Explicitly compute the matrices for the gates X tensor X and H tensor I. You may complain that we haven't done anything new so far. And you would be right. In fact, quantum gates that are obtained as the tensor product of 1-qubit gates can be seen as operations on isolated qubits that just happen to be applied at the same time. But wait and see. In the next subsection, we will introduce a completely different way of acting on 2-qubit systems, 1.4.3. The Kennard gate. By tacking tensor products of 1-qubit gates, we can only obtain operations that act on each qubit individually. But this just leaves us with a rather boring subset of all the possible 2-qubit gates. There are many unitary matrices that cannot be written as the tensor product of other simple matrices. In the 2-qubit case, probably the most important one is the controlled NOT, or controlled X gate, usually called the C0 gate, given by the unitary matrix begin PM matrix 1 and 0 and 0 and 0 0 and 1 and 0 and 0 0 and 0 and 0 and 1 0 and 0 and 1 and 0 NP matrix. It is illuminating to see how this gate acts on the elements of the 2-qubit computational basis. As you can easily check, we get C0, vertical bar 0 0 right angle, equals vertical bar 0 0 right angle, C naught vertical bar 0, 1, right angle equals vertical bar 0, 1 right angle. C naught vertical bar 1, 0 right angle equals vertical bar 1, 1 right angle. C naught E vertical bar 1, 1 right angle equals vertical bar 1, 0 right angle. This means that the value of the second qubit is flipped if and only if the value of the first qubit is 1. Or to put it in other words, the application of a NOT gate on the second qubit, that we call the target, is controlled by the first qubit. Now the name of this gate makes much more sense, doesn't it? In a quantum circuit, the C0 gate is represented as follows. Notice that the control qubit is indicated by a solid black circle, and the target qubit is indicated by the circle plus symbol. The symbol for an X gate can also be used instead of circle plus. Sometimes technical difficulties restrict the number of CANOT gates that can be actually implemented on a quantum computer. For instance, on a certain quantum chip, you may have the possibility of applying a CANOT gate targeting qubit 1 and controlled by qubit 0, but not the other way around. If you find yourself in such a situation, there's no need to panic. If you use the circuit HHHH, you are effectively applying a CNOT gate with target in the top qubit and control in the bottom one. And that's how you can save the day. The CNOT gate can also be used to interchange or swap the states of two qubits by using the following circuit, exercise 1.13. Check these equivalences in two different ways, by computing the matrices of the circuits and by obtaining the result of using them with qubits in states, vertical bar 0, 0 right angle, vertical bar 0, 1 right angle, vertical bar 1, 0 right angle, and vertical bar 1, 1 right angle. In any case, the most prominent use of the CNOT gate is, without a doubt, the ability to create entanglement, an intriguing property of quantum systems that we will study next. 1.4.4. Entanglement. Oddly enough, in order to define when a quantum system is entangled, we first need to define when it is not entangled. We say that a state vertical bar psi right angle is a product state, if it can be written as the tensor product of two other states, vertical bar psi sub 1 right angle and vertical bar psi sub 2 right angle, each of at least one qubit, as in vertical bar psi right angle equals vertical bar psi sub 1 right angle tensor vertical bar psi sub 2 right angle. If vertical bar psi right angle is not a product state, we say that it is entangled. For example, vertical bar 0, 1 right angle is a product state, because we know that it is just another way of writing vertical bar 0 right angle tensor vertical bar 1 right angle. Also, square root of 1/2 vertical bar 0, 0 right angle plus vertical bar 1, 0 right angle is a product state, because we can factor vertical bar 0 right angle on the second qubit to obtain 1 square root of 2. Vertical bar 0, 0 right angle plus vertical bar 1, 0 right angle equals 1 square root of 2. Vertical bar 0 right angle plus vertical bar 1 right angle. Tensor vertical bar 0 right angle. On the other hand, square root of 1/2 vertical bar 0, 0 right angle plus vertical bar 1, 1 right angle is an entangled state. No matter how hard you try, it is impossible to write it as a product of two 1-qubit states. Suppose, for sake of contradiction, that it were possible, then you would have 1 square root of 2 vertical bar 0, 0 right angle plus vertical bar 1, 1 right angle equals a vertical bar 0 right angle plus b vertical bar 1 right angle, c vertical bar 0 right angle plus d vertical bar 1 right angle equals a c vertical bar 0, 0 right angle plus d vertical bar 0, 1 right angle plus bc vertical bar 1, 0 right angle plus bd vertical bar 1, 1 right angle. But this forces a d to be 0 because we have no vertical bar 0, 1 right angle component in square root of 1/2 vertical bar 0, 0 right angle plus vertical bar 1, 1 right angle. Then either a equals 0, in which case a c is 0, or d equals 0, from which bd equals 0 follows. In both cases, it is impossible to reach the equality that we needed. Thus, it follows that the state is entangled. Exercise 1.14. Is square root of 1/3 vertical bar 0, 0 right angle plus vertical bar 0, 1 right angle plus vertical bar 1, 1 right angle entangled? And what about 1/2 vertical bar 0, 0 right angle plus vertical bar 0, 1 right angle plus vertical bar 1, 0 right angle plus vertical bar 1, 1 right angle? When measured, entangled states can show correlations that go beyond what can be explained with classical physics. For instance, if we have the entangled state square root of 1/2 vertical bar 0, 0 right angle plus vertical bar 1, 1 right angle, and we measure the first qubit, we can obtain 0 or 1, each with probability 1/2. However, if we measure the second qubit afterwards, the result will be completely determined by the value obtained when measuring the first qubit and, in fact, will be exactly the same. If we invert the order and measure first the second qubit, then the result will be 0 or 1 with equal probability. But, in this case, the result of a subsequent measurement of the first qubit will be completely determined. This still happens even if we separate the two qubits thousands of light years apart, as if one qubit could somehow know what the result of measuring the other qubit was. This curious behavior haunted many physicists during the 20th century, including Albert Einstein, who called it a spooky action at a distance, see 34. Nevertheless, the effects of entanglement have been repeatedly demonstrated in uncountable experiments. In fact, the Nobel Prize in Physics 2022 was awarded to Alain Aspect, John F. Clauser, and Anton Zeilinger, pioneers in studying and testing this phenomenon in practice, 10, 25, 41, 19. And very importantly for us, entanglement is one of the most powerful resources available in quantum computing. But entanglement is, by no means, the only puzzling feature of qubit systems. In the next subsection, we are going to mathematically prove that copying quantum information, an operation that you may have taken for granted, is not possible in general. These qubits are indeed full of surprises. 1.4.5. The no-cloning theorem. Another peculiar property of quantum systems is that, in general, they don't allow us to copy information. Surprising as this may seem, it is just an easy consequence of the linearity of quantum gates. To show why, let us be more precise about what we would need in order to copy information. For instance, with just 2 qubits, we would like to have a 2-qubit quantum gate U that will be able to copy the first qubit into the second. That is, for any given quantum state vertical bar psi right angle, we would need U vertical bar psi right angle vertical bar 0 right angle equals vertical bar psi right angle vertical bar psi right angle. Then U vertical bar 0 0 right angle equals vertical bar 0 0 right angle, and U vertical bar 1 0 right angle equals vertical bar 1 1 right angle. And by linearity, U 1 square root of 2 vertical bar 0 0 right angle plus vertical bar 1 0 right angle equals 1 square root of 2 U vertical bar 0 0 right angle plus U vertical bar 1 0 right angle equals 1 square root of 2 vertical bar 0 0 right angle plus vertical bar 1 1 right angle. We should highlight that the state that we have obtained is entangled, as we proved in the previous subsection. Nevertheless, notice that, in our original state, we can factor the second vertical bar 0 right angle out to obtain 1 square root of 2 vertical bar 0 0 right angle plus vertical bar 1 0 right angle equals vertical bar 0 right angle plus vertical bar 1 right angle square root of 2 tensor vertical bar 0 right angle. Then, in virtue of the action of U, we should have U 1 square root of 2 vertical bar 0 0 right angle plus vertical bar 1 0 right angle equals U vertical bar 0 right angle plus vertical bar 1 right angle square root of 2 tensor vertical bar 0 right angle equals vertical bar 0 right angle plus vertical bar 1 right angle square root of 2 tensor vertical bar 0 right angle plus vertical bar 1 right angle square root of 2, which is a product state. However, we had obtained earlier that U square root of 1/2 vertical bar 0 0 right angle plus vertical bar 1 0 right angle equals square root of 1/2 vertical bar 0 0 right angle plus vertical bar 1 1 right angle, which is entangled. This contradiction implies that, alas, no such U exists. This remarkable result is called the no-cloning theorem, and we should explain its meaning in a little more detail. On the one hand, notice that this does not imply that we cannot copy classical information. In fact, if vertical bar psi right angle is just vertical bar 0 right angle or vertical bar 1 right angle, we can easily achieve U, vertical bar psi right angle, vertical bar 0 right angle equals vertical bar psi right angle, vertical bar psi right angle by taking U to be the Keynote gate. On the other hand, the theorem applies to unknown states vertical bar psi right angle. If we know what vertical bar psi right angle is, that is, if we know a circuit that prepares vertical bar psi right angle, starting from vertical bar 0 right angle, then, of course, we can create as many independent copies of it as we want. However, if vertical bar psi right angle is handed to us without any additional information about its state, the no-cloning theorem shows that we cannot replicate its state in general. To learn more, The no-cloning theorem plays an important role in the security of quantum key distribution protocols, such as the famous BB84, introduced in 1984 by Bennett and Broussard, 13. After this brief detour, let's return to our study of 2-qubit quantum gates. In the next subsection, we will show how to construct many interesting 2-qubit unitary operations, whose action is controlled by one of their inputs. 1.4.6 Controlled gates. You may be wondering if, in addition to a controlled X or CNOT gate, there are also controlled Y, controlled Z, or controlled H gates. The answer is a resounding yes, and in fact, for any quantum gate U, it's possible to define a controlled U, or simply CU gate, whose action on the computational basis is CU vertical bar X right angle. Vertical bar Y right angle equals vertical bar X right angle. Vertical bar Y right angle, CU vertical bar X right angle. Vertical bar 1 right angle equals vertical bar X right angle. U vertical bar 1 right angle. CU vertical bar 1 right angle. Vertical bar Y right angle equals vertical bar 1 right angle. U vertical bar Y right angle. Exercise 1.15. Check that the matrix of CU is begin P a matrix 1 and 0 and 0 and 0 0 and 1 and 0 and 0 0 and 0 and U sub 11 and U sub 12 0 and 0 and U sub 21 and U sub 22 and P matrix, where U sub IJ sub I J 1 to 2 is the matrix of U. Check also that CU is unitary. What is the adjoint of CU? The circuit representation of a CU gate is similar to the one that we use for the CNOT gate, namely U, where the solid black circle indicates the control and the box with U inside indicates the target. Constructing a controlled gate is simpler than it seems, provided your quantum computer already implements rotation gates and the 2-qubit CNOT gate. In fact, from the decomposition in rotations that we mentioned at the end of section 1.3.4, it can be proved, see the book by Nielsen and Chuang, 69.9, Corollary 4.2, that any 1-qubit quantum gate U can be written in the form U equals e to the I theta, A, xbx, c, for some angle theta and gates A, B, and C such that ABC equals I. Then, the following circuit implements CU, R, C, B, A, T, Z. Sometimes, though, constructing a controlled gate is much easier. For instance, it can be shown that a controlled Z gate can be obtained from a controlled X and 2 H gates, as shown in the identity of the following circuits. Z, G, HH, exercise 1.16. Prove the preceding equivalence. We now have everything we need in order to construct our first 2-qubit quantum circuit. Let's get those qubits entangled. Exercise 1.18. Check that the basis state vertical bar J right angle is represented by a 2 to the n-dimensional column vector whose JTH component is 1, while the rest are 0. Hint: use repeatedly the expression for the tensor product of column vectors that we discussed in section 1.4.1, and the fact that the tensor product is associative. Deduce that any n-qubit state can be represented by a 2 to the n-dimensional column vector with unit length. If we decide to measure all the qubits of the system in the computational basis, we will obtain M with probability, vertical bar, a sub M vertical bar squared. If that is the case, then the state will collapse to vertical bar M, right angle. But if we only measure one of the qubits, say the jth one, then we will obtain 0 with probability. The sum from L and J sub 0, vertical bar A sub L vertical bar squared, where J sub 0 is the set of numbers whose jth bit is 0. In this scenario, the state of the system after measuring 0 would be the sum from L in J sub 0 A sub L vertical bar L right angle, square root of the sum from L in J sub 0 vertical bar A sub I vertical bar squared. Exercise 1.19. Derive the formulas for the case in which the result of the measurement is 1. Exercise 1.20. What is the probability of getting 0 when we measure the second qubit of 1, 2 vertical bar, 1, 0, 0 right angle, plus 1, 2 vertical bar, 0, 1, 0 right angle, plus square root of 1/2 vertical bar, 0, 0, 1 right angle? What will the state be after the measurement if we indeed get 0? Computing inner products of n-qubit systems in Dirac notation is very similar to doing it with 2-qubit systems. The procedure is analogous to the one we showed in section 1.4.1, but taking into account that, left angle psi sub 1 right vertical bar tensor dots tensor left angle psi sub n right vertical bar phi sub 1 right angle tensor dots tensor vertical bar phi sub n right angle equals left angle psi sub 1 vertical bar phi sub 1 right angle dots left angle psi sub n vertical bar phi sub n right angle. Exercise 1.21. Compute the inner product of vertical bar x right angle and vertical bar y right angle, where x and y are both binary strings of length n. Use your result to prove that and vertical bar x right angle sub x in 0, 1 to the n is indeed an orthonormal basis. Exercise 1.22. Compute the inner product of the state square root of 1/2 vertical bar 0, 0, 0 right angle plus vertical bar 1, 1, 1 right angle and 1/2 vertical bar 0, 0, 0 right angle plus vertical bar 0, 1, 1 right angle plus vertical bar 1, 0, 1 right angle plus vertical bar 1, 1, 0 right angle. We can now turn to the question of how to operate on many qubits at once. Let's define multi-qubit gates. 1.5.2 multi-qubit gates. Since n-qubit states are represented by 2 to the n-dimensional column vectors, n-qubit gates can be identified with 2 to the n by 2 to the n unitary matrices. Similar to the 2-qubit case, we can construct n-qubit gates by taking the tensor product of gates on a smaller number of qubits. Namely, if U sub 1 is an n sub 1 qubit gate and U sub 2 is an n sub 2 qubit gate, then U sub 1 tensor U sub 2 is an n sub 1 plus n sub 2 qubit gate, and its matrix is given by the tensor product of the matrices U sub 1 and U sub 2. Exercise 1.23. Obtain the matrix for the CC0 gate and verify that it is unitary. The Toffoli gate is important because, using it and with the help of auxiliary qubits, we can construct any classical Boolean operator. For instance, CC0 vertical bar 1 right angle vertical bar 1 right angle vertical bar z right angle equals vertical bar 1 right angle vertical bar 1 right angle vertical bar not z right angle, where not z is the negation of z, and CC0 vertical bar x right angle vertical bar y right angle vertical bar 0 right angle equals vertical bar x right angle vertical bar y right angle vertical bar x and y right angle. This shows that, with quantum circuits, we can simulate the behavior of any classical digital circuit at the cost of using some additional ancillary qubits, since any Boolean function can be built with just negations and conjunctions. This is somewhat surprising because we know that all quantum gates are invertible, while not all Boolean functions are. It then follows that we could make all of our digital circuits reversible just by implementing a classical version of the Toffoli gate. We will not be studying any other concrete examples of gates that act on 3 or more qubits, because in fact, we can simulate their behavior with circuits that only use 1 and 2 qubit gates. Keep on reading to know how. 1.5.3 Universal Gates in Quantum Computing. Current quantum computers can't implement every possible quantum gate. Instead, they rely on universality results that show how any unitary operation can be decomposed as a circuit that uses a reduced set of primitive gates. In previous sections, we mentioned, for instance, that any 1-qubit gate can be obtained by using just R sub z and R sub y rotations. It turns out that similar results exist for the general case of n-qubit quantum gates. To us, it will be important to know that, for any unitary operation, we can construct a circuit that implements it using only 1-qubit gates and the C0 gate. For this reason, we say that those gates are universal, in the same sense that, for example, negation and conjunction are universal for Boolean logic. This fact will be crucial for our study of feature maps and variational forms in connection to quantum neural networks and other quantum machine learning models. To learn more, in addition to 1-qubit gates plus C0, There are many other sets of universal gates. For instance, it can be shown that the three gates H, T, and C naught can be used to approximate any unitary operation to any desired accuracy, and they are universal in that sense. See section 4.5 of the book by Nielsen and Chuang, 69, for proofs of these facts and for more examples of universal gate sets. To illustrate how C0 and 1-qubit gates can be used to implement any other quantum gate, the following circuit shows a possible decomposition of the Toffoli gate targeting the top qubit. H, T, 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 H, T, T, T+++. Exercise 1.24. Verify that the preceding circuit implements the Toffoli gate by checking its action on the states of the computational basis. This concludes our review of the fundamentals of quantum computing. We've come a long way since the beginning of this chapter, but by now we have mastered all the mathematics that we will need in order to study quantum machine learning and quantum optimization algorithms. Soon, we will see all these concepts in action. Exercise 1.23. Obtain the matrix for the CC0 gate and verify that it is unitary. The Toffoli gate is important because, using it and with the help of auxiliary qubits, we can construct any classical Boolean operator. For instance, CC0 vertical bar 1 right angle vertical bar 1 right angle vertical bar, Z right angle equals vertical bar 1 right angle vertical bar 1 right angle vertical bar not Z right angle, where not Z is the negation of Z, and CC0 vertical bar X right angle vertical bar Y right angle vertical bar 0 right angle equals vertical bar X right angle vertical bar Y right angle vertical bar X and Y right angle. This shows that, with quantum circuits, we can simulate the behavior of any classical digital circuit at the cost of using some additional ancillary qubits, since any Boolean function can be built with just negations and conjunctions. This is somewhat surprising because we know that all quantum gates are invertible, while not all Boolean functions are. It then follows that we could make all of our digital circuits reversible just by implementing a classical version of the Toffoli gate. We will not be studying any other concrete examples of gates that act on 3 or more qubits, because in fact, we can simulate their behavior with circuits that only use 1 and 2 qubit gates. Keep on reading to know how. 1.5.3 Universal Gates in Quantum Computing. Current quantum computers can't implement every possible quantum gate. Instead, they rely on universality results that show how any unitary operation can be decomposed as a circuit that uses a reduced set of primitive gates. In previous sections, we mentioned, for instance, that any 1-qubit gate can be obtained by using just R sub Z and R sub Y rotations. It turns out that similar results exist for the general case of n-qubit quantum gates. To us, it will be important to know that, for any unitary operation, we can construct a circuit that implements it using only 1-qubit gates and the C0 gate. For this reason, we say that those gates are universal, in the same sense that, for example, negation and conjunction are universal for Boolean logic. This fact will be crucial for our study of feature maps and variational forms in connection to quantum neural networks and other quantum machine learning models. To learn more, in addition to 1-qubit gates plus C0, there are many other sets of universal gates. For instance, it can be shown that the three gates H, T, and C0 can be used to approximate any unitary operation to any desired accuracy, and they are universal in that sense. See section 4.5 of the book by Nielsen and Chuang, 69, for proofs of these facts and for more examples of universal gate sets. To illustrate how C0 and 1-qubit gates can be used to implement any other quantum gate, the following circuit shows a possible decomposition of the Toffoli gate targeting the top qubit. H, T, 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 H, T, T, T+++. Exercise 1.24. Verify that the preceding circuit implements the Toffoli gate by checking its action on the states of the computational basis. This concludes our review of the fundamentals of quantum computing. We've come a long way since the beginning of this chapter, but by now we have mastered all the mathematics that we will need in order to study quantum machine learning and quantum optimization algorithms. Soon, we will see all these concepts in action,